Hi, everyone. We're going to talk more about factorials and how they relate to principles of counting. You think you know how to count? Well, if you did well in our Math 119 statistics class, perhaps. We'll see. And also, simplifying factorials will be a key issue in Calculus 2, Math 151, when you're manipulating things like series. All right. Example. How many ways are there to order a standard deck of 52 cards? So imagine a deck of 52 cards, a random deck lying on the table. So it's not freshly opened, right? So how many ways are there for the deck of 52 cards to be ordered? These are called permutations. Or total permutations, since we're going to order all the cards. As opposed to partial permutations, where you just take and order some of them. We're going to order all 52 cards. Now, as you put the 52 cards on the table one by one, how many possibilities are there for the first card? Well, there are 52 cards, 52. We do not put this card back in the deck. How many cards are left for the second card you put down? How many possibilities are there left? Well, you've taken one card out. Whatever it is, you have 51 cards remaining that this card could be. Then, after these two cards are placed, whatever they are, how many possibilities are there for the third card? There are 50. I could go on and on, but I don't want to waste your money as a student. Eventually, you only have two cards left, right? Okay, and there are two possible. At one point down the line, there are two possibilities left. Okay, for this card, and then after you put down that second to last card, how many possibilities are there for the last card? Well, there should be only one card left in your hand, and it goes there. Now, for each of these 52 possibilities for the first card, there are 51 possibilities for the second card. Imagine a big, bushy possibility tree. So there are 52 branches in this first round on the possibility tree. For each of these branches, there are 51 possibilities for the second branch, the second card, and so forth. Big, bushy tree. How many total paths are there along this big, bushy tree? It's going to be 52 times 51 times 50 times times 2 times 1. That's going to be 52 what? 52 factorial. By the countdown scheme over here, remember, n factorial is the product of the integers from 1 to n. Or if you think of it as a countdown from n to 1. And I was looking at 52 factorial more in terms of the countdown. 52 factorial equals 52 times 51 times 50 times times 4 times 3 times 2 times 1. That's 52 factorial. Again, 52 possibilities for the first card, then 51 for the second card, then 50 for the third card, and so forth. So the number of ways that you can order the deck is 52 factorial, which, if you work it out, is about 8 times 10 to the 67th. That's an 8 followed by 67 digits, which is literally astronomical. Let's take a look at it. This is Mathematica, the big brother of Wolfram Alpha. Okay, let's work out 100 factorial. Now, I want to make a point. Oh, not, I'm sorry. We're going to do 52 factorial first. Let's do 52 factorial first. Now, I want to make a point here. Well, up here, when we first described and listed some factorials, look at this. It started off slowly and low, 1, 1, 2, 6, 24. This is going to be 120. It turns out that factorials grow fast. In fact, they grow faster than any exponential function, any fairly basic exponential function, because with a fairly basic exponential function, for example, 2 to the x, or 2 to the n, let's say, the discretized version, you're multiplying by the same number over and over again. Here, you're multiplying by bigger and bigger numbers. So n factorial grows even faster than 2 to the n, or 3 to the n, or in the long run, even something like 1,000 to the n. In the long run, point is, factorial grows very fast, eventually faster than any basic exponential. What is 52 factorial? It's massive. It's astronomical. Again, look at this. 52 factorial is this gigantic number. In scientific notation, it's more than 8 times 10 to the 67th, an astronomical number. Now, on your calculator, again, n factorial grows in value very fast as n grows. Many calculators can't even handle 100 factorial. I doubt yours can. I'll give you a moment. Get that calculator out. Try to get 100 factorial. Odds are you're going to get something like error or overflow. I would bet your calculator can't even handle it. Mathematica can. Let's try 100 factorial. Well, if you thought this was big, get a load of this. Wow. It takes a couple of lines here. I'll blow it up a bit. Oh, wow. Makes this look almost puny. Scientific notation. It's over 9 times 10 to the 157th. So we're talking over a number where you have a 9 followed by 157 zeros. This number is a 9 followed by 157 digits, in fact. Why do we have a bunch of zeros over here? These are actually zeros. This isn't rounding. Why are there a bunch of zeros here? Well, one reason why is that we know that we're multiplying by numbers like 10 and 20 and 30, but even something like a 2 times a 5 will give a 10, right? So there are a bunch of integers in here that'll multiply to a multiple of 10. These are massive numbers, beyond astronomical. In fact, if we were to Google, hey, let's just Google. Google, let me ask you something, Google. Let me ask you something. How many atoms are there in the universe? Okay, it is estimated that there are between 10 to the 70th, 10 to the 78th and 10 to the 82nd atoms. So maybe about 10 to the 80th atoms. There are about 10 to the 80th atoms in the universe, which is bigger than 52 factorial, but 100 factorial dwarfs that. In fact, this is on the level of like about the square of that. This is more like the square of that. It's ridiculous. All right. But in general, let's get back to the combinatorial interpretation. The number of ways to order n distinct items, the different possible orders called permutations, the number of total permutations of n distinct items is n factorial. When I say distinct, I mean no clones. So, for example, I don't allow things like sort of copies of cards, for example. I don't allow. The items must be distinct. Otherwise, you have problems if you have clones, right? Okay, although they can be managed at some level. Okay. Now, let's talk about another example involving a deck of cards, but this time we have a different idea going here.